So here's our defrost heaters and our heater safety and our defrost termination and fan delay. And here's our defrost timer that's completely connected. What they want to show you in this is that there's a slide right here. And this little solenoid that's all kinds of burn up with this one could activate this slide and take it out of defrost even though the time clock wasn't ready. So maybe you had a hot pull down earlier that day or a couple of them that week, and so you didn't really develop much frost as compared to the 2 weeks previous where no one hardly ever went into that freezer and you just got frost all over the place. Well, the timer has the ability, well, the little safety in there, if it trips, it's going to provide power to the solenoid. That's going to slide this over and break the connection to the defrost heater and remake the connection to the compressor so it can come back on. Here's our defrost pins. There's just little screws that go through there, and it trips an armature as it goes by. Our defrost clock motor, a lot of those will have a little sticker on the window, especially in refrigerators. You see how this is translucent. You can see the motor running. And that's a really quick way of diagnosing a defrost clock. Defrost clock and wiring. The following slide is a pictorial diagram of the electromechanical clock, the evaporator, and the controls. The color-coded wiring is illustrated is typical of most walk-in freezers. The sample system is in the freeze cycle. Does everybody still have this diagram? Is it in your book somewhere?
I imagine it's on 219.
Because eventually you are going to want to refer back to this. I promise. You know those labs that we have? Anyhow. So, here's our power or our neutral. Where is power here? Power? Yeah. Well.
It's on the picture in the book. It's missing from there though.
Yeah, it should be like right here,
Right.
I guess.
It's on there.
Well, we've got our power. 1 and 2 are connected. So right now, power is going through 2 to 4, turning on the evaporator and providing power to the thermostat. So if the thermostat should call for cooling, that's going to activate the liquid line solenoid back to neutral. The evaporator fan and back to neutral through the defrost termination fan delay. Ah, now they've given me my power wires. That's awfully nice of them. Defrost clock might also have heaters like we discussed. This is time initiated. The clock movement pushes the slide bar on the rear of the clock. The slide changes the switch contact positions from freeze to, how's this about here? Position from freeze to defrost. So, we've broken our contact here. There's no way for the solenoid to come on, and the fan can't get back to neutral either. If this should continue to expand, this little bimetal element, and connect with brown, that's going to hit X, which is going to energize the solenoid. And the solenoid is going to push this over, reestablishing the connection to the evaporator and the thermostat. As of right now, it's got it shut off. 3 3, 2. Yeah, if we go from 1 through 3, we'll go to the defrost heater and back to neutral. So as you see, we've kind of taken steps in complexity. This is eventually going to be in one of your labs, so I hope you've got a copy of this somewhere. Right there, the defrost heater is engaged. And now the defrost clock, well, is in termination. Nope, not yet. We haven't established neutral. We're waiting. Ah, here we go. Now we've got neutral 2x. Power is already going to the defrost solenoid. Now it has a path back to neutral, and that is going to break our connection to the defrost heater. The fan, however, will not be able to come on until the coil has got cold enough to remake the connection to the black wire. Because what we might have a 50-degree coil in a box we're trying to keep -20. Do we want the fan coming on when we have a 50-degree coil? No, let's let that coil get down to what? 30 at least. Switching from defrost back to freeze. When the defrost termination switch is warm enough, usually 55, the clock's defrost solenoid is energized. The solenoid mechanically moves the slide, switching the contacts out of defrost and back into freeze, as we saw just a minute ago. The fan is delayed until the temperature of the evaporator is down to approximately 25, they say. Pretty close enough. And here we go. We have lost connection to the solenoid. Our power is going through the evaporator fan, but it can't do anything else. But we still have the compressor running. Now that this bimetal coil has shrunk enough to allow power back to the black terminal, power can go through to 4 to the evaporator fan and circulate the air, while from 4 through the thermostat and solenoid are keeping the compressor on. Defrost termination and fan delay. The control terminates or ends the defrost. The temperature rise closes the contacts on the control. A controls delay fan starting after defrost. The temperature fall closes contacts on the control. Some coils have 2 separate controls. Others have a combination defrost termination, fan delay, single little unit on there. Some termination controls are adjustable. And there's what it looks like. It's got a little curve to be mounted on a pipe. You can see the black, the red, and the brown wire. So here's our red wire to neutral, the black wire from the fans, and the brown wire to the X terminal on the defrost motor. The diagnostic procedure for the control is to set for defrost termination at 55 and fan delay at 25. Above 55, red and brown is closed and red and black is open. Below 25, red and brown is open and red and black is closed. So you could diagnose this thing with a cup of ice water, couldn't you? Well, maybe. It's at least gonna be 32. You can get it 25 degrees or lower. You can test it one way and then dip it down there and see if it doesn't switch. Might need a little bit of salt in that ice water to get it to I think you can do it. And here's the basic construction of the thing. We've got our phase plate, the deflection plate, the push pin assembly, and you can see this thing has two contacts. A contact on top and a contact on bottom, being that it's a bimetal element. When it gets warm, it's gonna flex one way. When it gets cool, it's gonna flex the other way. It's just that simple of a device. Here we have an adjustable defrost termination control. I think I would have liked to see inside that more, but it's just a thermostat. That's all it is. And you'll notice the adjustable one. What do you figure is in this bowl? Maybe, but it would be some sort of
Air.
gas. It's going to be some sort of, what's in this bowl?
Refrigerant.
Refrigerant's in that bowl. So some sort of refrigerant is in this bowl. And that adjustable defrost termination control is going to weigh against its opening force, and then the force that you're probably adjusting the spring or position of the control in there. Evaporator temperature sensing bulb, defrost termination adjustable. However, the fan delay is fixed at about 25 degrees. So this is a combination, but you can adjust the fan delay. Electronic defrost clocks, more accurate than electromechanical. One-click clock fits many more applications. And here's, just like I was showing you, that's probably the most popular at this time. You've got the 1, 3, 2, 4, a neutral, an X connection, just like the old style clocks. Depending on the direction that you put these is when it's on or off. And you set the little timer right like that. It's got operating lights. If it's in defrost, easy wiring terminal strip compared to the old school. And this will switch right here between 120 and 240 volts. So it's has a lot of uses. You could see this as a defrost timer. You could see it inside an irrigation timer. You could see it controlling an entire chiller system or an entire boiler system. You might even see it as the time clock for parking lot lights. Then they've got digital defrost timers. They got a little, it's the same terminal strip. You come here, you set the little, how much you want on, how much you want off. And there's the current time of day. Each one of these little things is 15 minutes. Same thing here. So in many ways, this is that model gone digital. Timer controls. And then we have electronic sensors. They sense pressure, electronic pressure transducers, temperature with thermistors. There we go. There's a pressure transducer. There's a couple of different temperature transducers. Programmable boards for these smart control boards, automatically control temperature, superheat, and defrost based on pressure and temperature inputs. Now, you guys, we're in review, so I'm going through this a little bit faster, but is any of this bringing something to mind that we discussed last week?
External TXVs?
Automatic one.
The electronic TXV.
Yeah, electronic TXV. Yes, what's that?
You can have one board that does all this. It controls the TXV. It uses the TXV as a liquid line solenoid to pump down when it wants to. It controls the superheat maybe it has some sort of input on subcool as well. And it can also be controlled and said, you are in defrost from this time to this time. And it's gonna monitor that defrost, and it already has a transducer on the coil temperature. It's gonna be the one that says, hey, I think the coil's warm enough. Let's turn the air conditioning back on. And by the way, I've got control of the relay that runs the fan too. So when it gets cold enough, I'm gonna close that switch. So in a way, all those complex controls that we're learning now, because you need to know them, are starting to get more and more replaced by a central logic board. It happened first in the air conditioning industry, and it's starting to get to refrigeration, which is really handy with larger scale refrigeration. You know, if you want to change the temperature of a Walmart, you've got to call Bentonville. They're controlling the temperature of the refrigeration boxes as well. They know when something's gone down. They get an email alert. And that's part of the advantages of these smart control boards. It might look like this. You know, the newer ones would probably, and maybe this does, have a place for a daisy chain communications network to where it can say exactly what kind of conditions it's under. And then we have a remote smart control. And that's where we're getting into the little guy that can actually talk to a computer. And that's the end of evaporators.